Acoustic radiation forces in the ultrasonic range for non-contact excitation of nonlinear microstructures. First of all, please let me to have a definition about what is acoustic radiation force. The acoustic radiation force is a time-averaged force acting on an object in a sound field. Uh, uh, After impacting on an acoustic field uh, to an object, we have two types of waves. First, incident wave, and the second is scattering waves. The interaction between these two types of waves, incident waves and scattering waves, uh, around the object produce the acoustic radiation force. This force has many applications. For example, acoustic levitation, vibroacoustography, modal testing, and acoustophoresis. Acoustic levitation uh, uses to levitate many different type of tiny objects, spheres, and particles. Uh, this type of force, acoustic radiation force is stronger than other type of force. For example, stronger than optical radiation force and more applicable than magnetic forces, uh, because a vast type of uh, particle can be levitated by acoustic radiation force, and uh, there is no limitation than magnetic forces for this type of force. Vibroacoustography is important in mm, biology to take picture from internal uh, body tissues and organs. Modal testing and non-contact excitation is another application of acoustic radiation force. We can obtain resonance frequency mood shapes of very tiny structures, and acoustophoresis is important in manipulating of different types of particles to separate them from each others. We have some mathematical formulation of acoustic radiation force. This The theoretical aspect of acoustic radiation force is uh, in many literature starts with this equation. This equation in continuum mechanics is the in Eulerian coordinate is the momentum equation. In Eulerian coordinate, because the coordinate is not fixed, the derivative with respect to time is not very simple. It is the derivative with respect with time, and also we can uh, replace the stress tensor with hydrostatic pressures. And finally, we have this equation as a momentum equation. We have other summation and other formulation here. For irrotational fluid, we can also find a potential function. The gradient of potential function is velocity. From and from This is the momentum equation from the previous page, and we can replace the phi, the uh, potential function of velocity, into the momentum equation. From the first law of thermodynamics here, we can find in for adiabatic motion, we can rewrite the momentum equation, and also we can replace the we can find enthalpy here, and after replacing enthalpy into the momentum equation, we can and also using the Taylor series and expanding p around the w enthalpy, we can finally find the pressure. The pressure is very important here. This is the mean excess pressure. The mean excess pressure is used to find the acoustic radiation force, because we know that the integral of the pressure around the body, the surface integral, results the forces. Another important component in acoustic radiation force is Reynolds stress. In many literature, mm, researchers ignores Reynolds stress, but it is also important. This is the Reynolds stress, and the Reynolds stress comes from the continuity equation. Uh, in for static acoustic radiation force, by combining these equations, we can find the uh, stress radiation tensor. The stress radiation tensor is very important to find acoustic radiation force. The first part of this tensor is mean excess pressure, and the second part is Reynolds stress here. For acoustic radiation force, I listed some of researchers who worked about this type of force: Kings, Yoshiaka and Kawashima, Gorokov, Dainakov, Hezagawa, and other researchers find it. They found the acoustic radiation force for spheres, for cylindrical objects, and with different boundary conditions, and but in theoretical aspect of static acoustic radiation force, the theories is very limited to very simple objects, for spheres, for cylindrical objects. Dynamic acoustic radiation force comes from the interaction between two waves instead of one wave in static radiation force. The interaction between two waves in the air produce dynamic acoustic radiation force. In this type of force, the phi, the phi, the potential function of velocity change in the time, and also the radiation force as a result is a harmonic radiation force, and it is dynamic acoustic radiation force, and the dynamic radiation force frequency depends on the difference between two waves frequency. In this research, there are some research questions. First of all, the modeling the dynamic acoustic radiation force is in COMSOL is in the first research question. How we can model and simulate for dynamic acoustic radiation force in COMSOL. There are some articles about modeling and simulation the static acoustic radiation force in finite element softwares, but there is no any simulation about dynamic acoustic radiation force simulation in in finite element software such as COMSOL. Applying acoustic radiation force on nonlinear macrostructures and obtaining the response experimentally, numerically, and analytically have not been investigated by any researchers. And the second and the third, developing new acoustic lenses to generate non-contact excitation signals with complex spatial and temporal profiles. The spatial and temporal profiles of acoustic radiation force is not be controlled uh, by researchers, and it has not been investigated by researchers. Uh, and we can by developing new lasers can steer and find more application of acoustic radiation force, and finding a broadband frequency range for this type of lenses also is important, and complementing experiments to verify the data is another effort is valuable for this research. Thank you.